Good morning, you wake up, you walk into the bathroom, you flip on the light, grab your toothbrush, and look straight ahead. And there he is, that other guy. You've known him your whole life. You trust him to shave your face. You check him to see if there's spinach stuck in your teeth. But have you ever truly stopped to think about what exactly you're looking at? Because if you let yourself think about it for even 10 seconds, it starts to bother you. It bothers you a lot. Let's try an experiment right now. Raise your right hand. Wave hello to that guy in the glass. What does he do? He raises a hand. But which one? His left one. You tilt your head to the right. Or he tilts his to the left. You wink your right eye. He winks his left. Fine, you say. That's obvious. The mirror swaps left and right. We've all known this since kindergarten. It's called a mirror image. But wait a minute, stop. Why did the mirror decide to swap specifically left and right? Look again. Your head is at the top. And for him, in the mirror, the head is also at the top. Your feet are at the bottom, and his feet are at the bottom. The mirror didn't flip you upside down. Gravity works the same way. The ceiling is still there. And this is where the headache begins. Why does this piece of glass with silver coating have such strange selectivity? Why does it say, okay, I'll flip the horizontal axis, left becomes right, but the vertical axis, up and down, I won't touch. I like that one. Does the mirror have preferences? Or maybe is it about our eyes? A lot of people tell me, Dick, it's simple. Our eyes are placed horizontally. Ears are placed horizontally. We are creatures of horizontal symmetry, so the mirror gets confused horizontally. Sounds smart, but that's complete baloney. Imagine you lie down on the floor, on your side, in front of a big mirror. Now your eyes are arranged vertically, one above the other. You've aligned yourself with the line of gravity. But if you wave your hand, the mirror still confuses left and right relative to your body, but it doesn't confuse top and bottom. Even if you stand on your head, the mirror dutifully flips you over, but the left hand still remains mirrored. It haunts you. It seems like such a simple question that it's almost embarrassing to ask. But I'll tell you a secret. The greatest physicists have racked their brains over this over a cup of coffee. Why does symmetry work exactly like this? Let's take a book. Any book from the shelf. Hold it up to the mirror. Can you read the title? No. The letters are turned inside out. The words go backward. Alice in Wonderland turns into a cipher. The mirror ruined the text from left to right. But notice, it didn't flip the letters upside down. The letter A is still standing on its legs, not on its point. And what the heck is going on? Does the mirror know physics? Does it sense where the center of the Earth is and respect gravity, refusing to flip things vertically? No. We can fly into space, where there is no up and down, take a mirror with us, and it will still behave just as stubbornly. We are facing a fundamental mystery, and the answer to it doesn't lie in the glass, and not even in the light. The answer lies in how your brain builds a map of reality. You see, when you look in the mirror and say, it changed left and right, you're making a mistake. A deep psychological mistake. The mirror didn't change anything. It was you who mentally did something to yourself to stand in the place of that guy in the glass. You think the mirror is a painting. But the mirror is not a painting. And to understand what is actually happening, we need to stop thinking like people looking at their faces and start thinking like geometers. We need to deal with the third dimension, with what we usually forget about when brushing our teeth, with depth. All right, forget about mirrors. Forget about the bathroom. Imagine a glove, a regular leather baseball glove. Now imagine you take this glove and turn it inside out. All the seams that were inside are now outside. The leather that was outside is now inside. Can you do that? Yes, easily. But now try to do something else. Without changing anything in the structure of the glove, without making holes in it, without cutting the seams. Try to turn a right glove into a left one. You can't do it. You can rotate it however you want. You can spin it in 3 dimensions. But you will never, do you hear me? Never be able to force it to become left unless you poke a hole and turn it inside out. Right and left gloves are objects with different orientations. They are not symmetrical. They are mirror images of each other. And here's what the mirror does. It doesn't change left and right. It changes front and back. It's as if it takes you, flattens you like a pancake, and then flips you over. This is called inversion. Inversion along the z-axis, where the z-axis is the line that goes from your face to the mirror. Imagine standing in front of a mirror. You take a step forward, your reflection takes a step backward. You reach out your hand to touch the glass. Your reflection also reaches out a hand to touch the glass. Your hands meet at one point. But what is that point? It is a point that is exactly in the middle, between you and your reflection. The mirror is like it takes everything in front of you and projects it behind itself to the same distance. It creates an exact copy of you, but turned back to front. Now back to our left-right problem. When you look in the mirror and see that your right hand is turned into a left one, it happens because your brain automatically tries to imagine itself in the place of your reflection. You try to mentally step into the mirror. And here's the catch. To do that, you need to perform a mental inversion. You need to imagine that you were squashed like a fly on a windshield and then flipped over. That is exactly why it seems to you that the mirror swapped left and right. In reality, it swapped front and back. But why does our brain cling so stubbornly to this left-right idea? Why is it so hard for us to imagine ourselves turned inside out? I think it has to do with how we move in the world. We walk forward, we look forward, we have a face that looks forward, we have a back that we usually don't see. We are used to the front part of our body being the main part. And when we see a reflection that swaps front and back, our brain tries to fix it by performing a left-right inversion, because that seems more logical to it. It's like an optical illusion. Your brain sees one thing but interprets it differently based on its experience. But is this explanation enough? Does it show that we truly understand symmetry? Can we convey this understanding to someone else who doesn't see the world with our eyes? Imagine you need to explain what left is to a creature from another planet. A creature that has never seen a mirror. A creature that has neither a right nor a left hand. How would you do it? Now that we've sorted out your reflection in the bathroom, let's get into something more serious. Let's get into physics. Imagine that you and I are engineers, and we decide to build a clock, a regular mechanical clock, with springs, gears, and a pendulum. We build it here in our lab. It ticks, the hands go to the right, 1, 2, 3, everything as usual. Now imagine that we build exactly the same clock, but following blueprints that we see in a mirror. Every part, every screw, we make mirrored. If in our clock the spring is wound clockwise, then in that second clock it will be wound counterclockwise. If the teeth of the gear tilt to the right, there they will tilt to the left. We assemble this mirror clock. We wind it up, and here's the million-dollar question. Will it work? Don't rush. Think. Will it tick at the same speed? Will it fall apart? Will the mechanism jam? Physics' answer is a solid yes. It will work perfectly. Of course, the dial will be reversed, and the hands will run backward, but the mechanism itself, the physics of the process, will function flawlessly. Why? Because Newton's laws couldn't care less about which is right and which is left. The force with which the spring pushes on the gear does not depend on which way the spiral is wound. Gravity, which pulls the pendulum down, doesn't ask, "Hey buddy, are you swinging left or right?" It doesn't care. This is a fundamental principle of classical physics. Nature is symmetrical. You can take any physical process, absolutely any. The collision of two billiard balls, an explosion of dynamite, the flight of a comet around the sun. Film it with a camera, and then play this movie in mirror reflection. No one, not a single professor, not a single genius, will be able to tell you which movie is real and which is reflected. In the reflected world, billiard balls scatter at the correct angles. The laws of conservation of energy and momentum work exactly the same way. Gravity pulls planets with the same force. If we lived in a mirror copy of the solar system, where the Earth spins the other way, we wouldn't even notice the difference. Our equations wouldn't change by a single letter. This is called parity invariance. A fancy word, but the meaning is simple. Physics has no favorite hand. God is ambidextrous. He writes laws that work equally well in the ordinary world and in the looking glass world. It would seem this is beautiful. Symmetry is beautiful. It is soothing. The world is harmonious and balanced. But this beauty has one nasty side. If all laws of physics are symmetrical, if nature doesn't distinguish between left and right, then we have a huge problem with communication. Imagine you're sitting by a phone, and you've reached someone very far away. A guy who lives so far away that he has never seen Earth, never seen us, and doesn't even know where the solar system is. We want to make friends. We want to tell him about us. But how do we explain the simplest things to him if our words mean nothing to him? Let's play a telephone conversation. Imagine we finally did it. We built a powerful transmitter, pointed it at the sky, and contacted a guy from Alpha Centauri. Let's call him Alf. We've never seen Alf. Alf has never seen us. Between us lies 4 light years of emptiness. We can't send him a package. We can't show him a picture because a picture is a stream of data, and to assemble it, he needs to know if we scan the image from left to right or right to left. All we have is voice, radio waves. At first, everything goes great. We teach him to count. Beep is 1, beep beep is 2. We explain chemistry to him. Hydrogen, 1 proton, 1 electron. He answers, got it. Physics is the same everywhere. Chemistry is the same everywhere. We can even explain dimensions to him. We talk about the wavelength of light we use for communication, and he understands what a meter is. We can explain temperature. Moreover, we can easily explain to him where up is and where down is. We say, Alf, drop a rock. Where it flies, that's down. Gravity gives us a perfect reference axis. We feel like geniuses. We found a common language with an alien intelligence. And so, in our joy, we decide to describe ourselves to him. Well, we say, we are these bipedal creatures, about 2 meters tall, and most importantly, we have a pump inside, a heart, and it is located on the left side. And then silence hangs in the speaker, and then Alf asks, on the left? Where's that? You freeze. You scratch your head. How do you explain left? You say, well, it's simple. Face north. Then east will be on the right and west on the left. Alf laughs. What is north? I don't have your North Star here. I'm on another planet, remember? You start to get nervous. Okay, forget the stars. Take a magnet, a regular magnet. It has a north pole and a south pole. Stop. How does he know which pole is north? Magnets don't come with labels created by nature. We humans just painted one end blue and the other red. For Alf, it's just a piece of metal. You say, fine, let's make an electromagnet. Take a wire, run a current through it, and the magnetic needle will deflect in a certain direction. That's the right-hand rule. This seems like salvation. The right-hand rule is the foundation of electrodynamics. You think, aha, I got him now. But let's break this down. You tell him to wind a coil. Okay. You tell him to run a current. Okay. But which way does the current flow? You say, from plus to minus. And he asks, what is plus? You'll have to explain that minus is the charge of an electron. But how do you know that his electrons are the same particles as yours? What if he is made of antimatter? What if his electrons have a positive charge? Even if he is made of ordinary matter, the problem remains. All physical phenomena related to magnetism and electricity are symmetrical. If you build a mirror laboratory, mix up all the wires, swap left for right, the compass needle will still turn exactly as the formulas predict. You can bang your head against the wall, but you won't find a single classical experiment, not with gyroscopes, not with pendulums, not with magnets, that would give you a unique, absolute definition of the left side. Any explanation you give will require a reference standard. Left is where my mole is. Left is where cars drive in Britain. But Alf can't see your mole and has never been to London. This is called the Ozma problem. And for a long time we thought it was unsolvable. We thought left and right were just conventions invented by humans, and the universe didn't give a damn about them. We thought that if we met an alien, we could never know if he sees the world the same way we do, or as in a mirror. We were sure of this. It was dogma, the law of conservation of parity, the foundation of science. But then someone decided to test this foundation for strength, and what they found made all the physicists of the world drop their coffee cups. It was 1956. Physics was quiet and peaceful. We thought we knew the rules of the game. We were sure that nature was this proper lady who looks in the mirror and sees her exact copy there. But two young guys, Li and Yang, started asking uncomfortable questions. They looked at the strange behavior of some particles and said, "Hey, did we actually check if symmetry works in the weak interaction? Or did we just decide it works there because it's prettier that way?" No one took them seriously. The great Wolfgang Pauli even said, "I do not believe that God is a weak left-hander." But Li and Yang convinced Madame Wu, a brilliant experimentalist, to check it. Madame Wu took the isotope cobalt-60. It's a radioactive metal. It is unstable. It decays. When it decays, it spits out an electron. This is called beta decay. But just looking at a chunk of cobalt is useless. The atoms there are looking every which way, like a crowd at a bazaar. To see order, they need to be lined up. Madame Wu cooled the cobalt almost to absolute zero, so the atoms would stop shivering from heat. Then she turned on a massive magnetic field. Cobalt atoms are little magnets. They have spin. They rotate like tiny spinning tops. Under the influence of the field, all these tiny atomic tops lined up in a single row. All their axes of rotation began to point in one direction. The stage is set. The lights are dimmed. If nature respected symmetry, then electrons during decay should fly out with equal probability in both directions along the axis of rotation, up and down, or left and right. It doesn't matter. The main thing is equally 50-50. Because if you look in a mirror at a spinning top, it still remains a spinning top. The mirror shouldn't influence where the particle flies out. Madame Wu started the counters, and the world turned upside down. It turned out that electrons, those little rebels, couldn't care less about symmetry. The overwhelming majority of them flew out in only one direction, in the direction opposite to the spin. Imagine you have a cannon. You spin its barrel. And suddenly it turns out that the shells are flying out not from the muzzle, but from the breech. Always. It was a shock. It was a scandal. Parity is violated, screamed the headlines. Nature turned out to be asymmetrical. At the deepest, most fundamental level, in the heart of matter, the universe distinguishes up and down, left and right. Imagine looking at a clock, and it's running counterclockwise, just because you cooled it down. That's how strange it was. A mirror image of the Wu experiment is impossible in our world. If you reflect this setup in a mirror, the rotation of atoms, spin, will reverse, but the direction of electron emission in the mirror will remain the same. In the end, you get a physically impossible picture. Electrons would fly out in the direction of the spin, but in our world, they fly out against it. The mirror lies. The looking glass world is a different universe with different laws. And do you know what this means? It means we can call Alf. We grab the phone and yell, "Alf, listen here. Forget about magnets and hands. Take cobalt-60. Cool it down. Put it in a magnetic field. Look where the electrons fly. That side where they fly out from. That is down. The absolute universal down. And now stand so that this down is at your feet and look at the rotation of the atoms." Now we can define left and right, absolutely. We found the Rosetta Stone of the universe. We defeated the Ozma problem. But victory brings new questions. Why? Why did the universe choose specifically this option? Why do electrons fly to the left and not to the right? Why did God turn out to be left-handed? To understand this, we need to dive even deeper. We need to look at the bullet itself. We need to talk about screws, threads, and why the neutrino is the loneliest ghost in the world. Take a rifle, look into the barrel, just make sure it's not loaded, please. What do you see there? You see rifling. Spiral grooves that run inside the barrel. Why are they there? To make the bullet spin. When the bullet flies out, it spins. This stabilizes its flight. But here's the question. Which way does it spin? Clockwise or counterclockwise? That depends on how the master cut the barrel. Most rifles make the bullet right-handed. In the quantum world, particles also have rotation. We call it spin. It's not exactly the same as a spinning top, but for our story, it's enough. The particle flies and spins, and this is where the magic begins. In the cobalt experiment, there is another player involved, a ghost. a particle that is almost impossible to catch. The neutrino. When an atom decays, an electron flies out. And a neutrino, well, or an antineutrino, but let's not complicate things. And it turned out that these guys are the pickiest creatures in the universe. Imagine you come to a factory that makes screws, regular screws. You pick up one, it has a right-hand thread. You pick up another, right. You dig through the whole warehouse, millions of screws, and they all screw into the right. You ask the director, "Do you have any left screws?" And he looks at you like you're crazy. Left screws don't exist. That's a myth. That is how the neutrino is built. In our universe, all neutrinos are left-handed. Every single one. Imagine a bullet that always, absolutely always, rotates to the left relative to its movement, like a left-handed screw. If you stick your left hand out forward and stick up your thumb, the thumb shows the direction of flight, and the other fingers show where it rotates. Always the left hand, never the right. It is astounding. Now look at this in a mirror. In the mirror, the left hand turns into a right one. The left-handed screw becomes right-handed. And this is why the mirror world is impossible. If you look in a mirror at a flying neutrino, you will see our right-handed neutrino. But we checked, that in our universe, there are no such animals. Nature simply didn't issue them a license to exist. The mirror shows you a particle that doesn't exist in physical reality. The mirror shows you an impossible object. Before the Wu experiment, we thought space was just an empty stage and a box in which the action takes place. And this box doesn't care what happens inside it. But it turned out that the stage itself has a structure. Space is not an empty box. It's more like a twisted fabric. The very laws of weak interaction, the force that governs decay, have built-in rifling. They only work with left screws and ignore right ones. It's like trying to screw in a light bulb. If you have the correct light bulb, it lights up. If you try to screw in a mirror light bulb, it simply doesn't fit into the socket. The universe gives it no contact. We call this chirality. From the Greek chir, hand. The universe is chiral. It is handed. And this changes everything. We no longer live in a boring, symmetrical world. We live in a world with character. In a world that made a fundamental choice at the very beginning of time. And now that we know that atoms and particles have this left bias, a frightening question arises. We are made of atoms, after all. We are made of particles. Does this mean that this leftness rises higher, from the quantum level to our bodies, to our food, to life itself? If the universe is a factory for left-handed screws, what happens if we try to assemble a human out of them? Let's come down from the heavens to the earth. Let's go into the kitchen. Take the sugar bowl. Look at these white crystals. This is sucrose. If we look at a sugar molecule under a very strong microscope, we will see a spiral. It is a complex, three-dimensional structure, twisted to the right. Chemists call this D-glucose, from the word dexter, right. But we chemists are tricky guys. We can go into the lab and synthesize a molecule that will be the exact mirror image of this sugar. We'll call it L-glucose, left. It has the same atoms of carbon, hydrogen, and oxygen, the same bonds, the same density. It melts at the same temperature. If you put a spoonful of this mirror sugar in your tea and taste it, it will be sweet. Your taste buds on your tongue are pretty rough sensors. They just scream sweet when they feel a certain shape. They don't care about orientation. But here's what happens next. You drink this tea. The sugar hits your stomach, and there it meets enzymes. These are little biological machines whose job is to break down food to give you energy. And this is where the drama begins. Your enzymes, they are like gloves, or like keys to locks. And they're all, absolutely all in your body. Chiral. They have a shape tailored for right sugar. The enzyme swims up to the mirror sugar molecule, tries to grab it, but it doesn't fit. The angles stick out the wrong way. The key doesn't fit the keyhole. The enzyme swims away in confusion. The sugar passes through you in transit without giving up a single calorie. Now imagine this on a scale. Imagine we flew to another planet, to a mirror planet. There the grass is green, cows moo, water is wet. You pick an apple and eat it. It's delicious. You drink the milk of local cows. It's fresh. You stuff your belly full. But a week later you die. You die of starvation with a full stomach. Because all the biochemistry of this planet is mirror image. Your proteins can't absorb their proteins. Your enzymes can't break down their fats. To your body, all this food is just sand. It's scary, isn't it? We are used to thinking that food is just matter, but food is geometry. Life on Earth made a choice a long time ago. No one knows why. Maybe it was an accident. Maybe a meteorite with left amino acids fell into the primordial soup. But the fact remains, all life on Earth is built on left-handed amino acids and right-handed sugars. We are all left-hand threads. From a bacteria to an elephant, from a virus to the President of the United States, we all use the same standard set of Lego bricks. I have another favorite example, mint and caraway. There is a substance called carvone, a simple molecule. If you assemble it in the right version, it smells like caraway, the kind they put in rye bread. But if you assemble the exact same molecule in a mirror image, left, carvone, it smells like mint, spearmint gum. The smell is different. The substance is the same. Why? Because you have receptors in your nose. And these receptors are also chiral. It's as if you had molds in your nose. The right molecule falls into the right mold, and the brain gets the signal bread. The left molecule falls into the left mold, or gets stuck differently, and the brain screams mint. You smell geometry with your nose. So symmetry is not an abstraction from a textbook. It is a matter of life and death. It is the taste of your breakfast. And this brings us to the most important final question. We found out that physics distinguishes left and right, thanks to cobalt. We found out that biology distinguishes left and right, thanks to sugar. So now we are ready to meet Alf. We can explain everything to him. We can say, build a rocket, come to us, we know how to shake hands. We found a common language. We defeated chaos. Or did we? So, we've come a long way. We started with your reflection in the mirror, which teased us with its mystery. We turned a glove inside out. We started a clock running backward. We froze cobalt and forced it to reveal the secret of the left hand of the universe. And now we stand on the threshold of the greatest moment in history. We are back on the phone. We say to Alf, listen, buddy, we figured it all out. Take cobalt. Look where the electrons fly. That is down. Turn so that down is at the bottom. And then that hand which is on the side of your heart, that is the left hand. Alf answers, got it. Left is where the heart is if standing on the cobalt bottom. Thanks, Earthlings, I'm taking off. We prepare for the meeting. We build a landing pad. We hang flags. The orchestra rehearses the anthem. We agreed with Alf on one important cultural thing. When he gets out of the ship, we will shake right hands. This is a universal sign of peace. Since now we gave him the perfect physical definition of right and left, there can be no confusion. The ship lands, or the smoke clears. The hatch opens. But here, as a physicist, a chill runs down my spine. Because there is one thing we didn't check. One little detail we forgot to ask about in the euphoria of discovery. What if Alf is made of antimatter? We know antimatter exists. Positrons, antiprotons. We create them in labs every day. They behave almost exactly like ordinary matter. They have the same chemical reactions. Anti-Alf will look exactly like regular Alf. He will speak the same way. His ship will shine the same way. But there is one problem. Remember we said the mirror swaps left and right? And that physics in the mirror doesn't work? Because of cobalt? Well, physicists discovered an amazing thing. If you do two things simultaneously, reflect the world in a mirror, swap left for right, and replace all matter with antimatter, swap charge, then symmetry returns. This is called CP symmetry, charge and parity. If you take anti-cobalt, the decay process in it will be a mirror reflection of our decay. In our world, electrons fly down. In the antimatter world, positrons from anti-cobalt will fly up, relative to the spin. Nature is like saying, I violate left-right symmetry, and I violate plus-minus symmetry. But if you flip both, I become symmetrical again. And here is the horror of the situation. If Alf is made of antimatter, he will perform the experiment with anti-cobalt. He will see particles flying in the other direction. But he will call that direction down because we told him to. His definition of down will be upside down compared to ours, which means his definition of left and right will also be flipped. He will think he did everything correctly. He will follow our instructions to the letter. But because he is made of anti-stuff, his right is our left. And there he stands on the ramp. The crowd freezes. The president of Earth steps forward and extends his right hand. Alf smiles, if he has a mouth, and extends his hand to meet him. In this moment, a split second before contact, you must look very closely. Which hand is he extending? If he extends his right hand, from our point of view, hooray, he is made of matter. We are saved. Geometry worked. Physics worked. We can drink champagne. But if he extends his left hand, don't think he's just rude. Don't think he got confused. He didn't get confused. He is honestly trying to shake your right hand based on his inverted anti-material world. But if he extends the left one, it means he is made of antimatter. And if you touch him, if you commit to this handshake, annihilation will occur. An amount of energy will be released that hasn't been released since the creation of the world. The explosion will be visible from Proxima Centauri, of Earth, of Alf, of the President, and of the landing pad. Only pure, blinding light will remain. So, my friends, here is my final advice on symmetry. Study physics, admire mirrors, rack your brains over neutrinos. But if an alien ever flies to you whom you taught left and right over the phone, and upon meeting he extends his left hand, don't shake it, just run. Thanks for your attention. See you tomorrow.